The subject of recursive subdivision has been touched in several videos on YouTube so far, but I feel that the technique described here is easier to wrap your mind around, executes very fast, even for large numbers of faces, and works flawlessly for quads and triangles alike. These are some of the tests I've done so far. A lot of you have asked me how it's done, and that is exactly what I will try to explain in this video. The core idea is simple. Here we have a single quad face which we duplicate and manipulate so that two of the points constantly move from their original place to the position of their horizontal neighbors. On the duplicate face, we move the other points to the same amount in the opposite direction, giving the impression of dynamic subdivision. Same things for the vertical direction. We can apply this operation several times in a repeat zone, thus subdividing each face further with each iteration. Before starting with the actual tutorial, let me first reveal a great feature added to Blender 4.1 which will help a lot of users in debugging their setups. It's the ability to view attribute values as numbers in the 3D viewport. To activate it, simply go to the Overlay pop-up menu and check the Attribute Text option. And while we're here, let's also uncheck the Color Opacity option and activate the wireframes for faces and edges. Let's start with a simple 3x3 grid. Split the edges, and for visualization purposes, let's scale down the faces somewhat. Add a reroute node and group it inside the node group. Call the group Recursive Subdivision. We'll wrap this node group inside a repeat zone later. I could have built the setup directly inside a repeat zone, but I like to keep the node tree clean and easy to understand, so I chose to group all the nodes that form a certain function. To move the points around, we'll use the Set Position node with a mix vector attached into the position input. This will mix the current position of each point with another vector, in this case 0, 0, 0. Play with the mixing factor and you see the points slide towards the center. This is because we're feeding them the same target, the origin vector. As you know, the diamond socket with a hole means that the node also accepts a field as an input. That is a sequence of vectors, one for each point. Points are sorted by their index number, so let's visualize those indices first. Holding Ctrl plus Shift and clicking on the Group Input node generates a Viewer node. Feed an index node to its input and watch the indices as numbers on the 3D view. The automatic mode actually is the same as the point mode, so we're currently viewing the point indices. What we want to happen is for each point to have a target of its own, so that point 0 and point 10 both target point 0, and point 9 and 11 both target point 9. In the same manner, we should have points 1 and 12 aim at point 1, 2 and 14 at 2, 4 and 7 at 4, 5 and 8 at 5, and so on. But how do we do that exactly? Is there a rule or a formula that returns us that sequence? These numbers seem pretty much random to me too. There is in fact another way, a more straightforward way to generate such a sequence. We could sort the points based on the face corner indices. You can clearly see that the face corners are sorted in a much more ordered way. The indices increase sequentially, going in the counterclock direction, without skipping numbers. So each face has 4 consecutive indices. This will help us a lot in defining the rule to generate a sequence of indices for the points that will serve as the targets for the new positions. Let's focus on the first face for the moment. The sequence of indices we're after as target is 0033. This way, points 0 and 3 stay in place, but points 1 and 2 move towards 0 and 3. Add a modular node, set the value to 4. This will loop the sequence to a range from 0 to 3. Continue with the snap node with a value of 2. Snap is the same as dividing by 2 and flooring the result. Now, the sequence reads 0, 0, 2, 2. Checking the clamp option on the snap node will limit the result to a maximum of 1. Now it's only a matter of multiplying it by 3, and we got 0, 0, 3, 3. Exactly the sequence we need. Well, not quite, because this way the points of all faces will overlap with the first face. We need to offset each set of 4 face corners by the face index. Let's branch out yet another snap operation with the value set to 4. This will increase each set of 4 numbers by 1. Adding both results together should now return the right sequence of numbers. Feed it to the index input of an Evaluate@Index node. Set the data type to vector and switch the domain to face corners. The attribute to evaluate is position. Connect the resulting field into the empty input of the mix vector node. Now, playing with the mixing factor, we can see the polygons shrink horizontally to the left. But we're only halfway there. We need to set up the other half so that when one side shrinks, the other one expands. We'll continue from what we've built already. Ctrl plus Shift click on the snap node will give us the sequence 0, 0, 1, 1. Adding 1 to it will result in 1, 1, 2, 2. This sequence will keep points 1 and 2 in place and slide points 0 and 3 instead. Let's add the result to the snapped index by 4 and test the result. Replace the index input field of the Evaluate@Index node and play with a mix factor. Now we have both faces ready, so their edges slide horizontally. Frame these nodes and call them left, right. What about a vertical option? Let's take care of that now. Start from the same steps, an index field, evaluate it in the face corner domain, followed by a modular operation by 4, together with a snap by 2 and clamped to 1. The same steps earlier returned us a sequence of 0, 0, 1, 1. If we add 1 to the index number before the modular operation, the sequence changes to 0, 1, 1, 0. Again, let's offset each 4 set of point indices by a face index. Branch off a snap node with a value of 4 and add the results together. This series of indices will move the division line towards the bottom points. At last, a sequence that will move the line towards the top points. It should read 3, 2, 2, 3. The top points stay in place while the bottom ones move towards the top. From the bottom snap operation, add a math node and subtract the result from 1. This will give you 1, 0, 0, 1. Add 2 to this result and you will get 3, 2, 2, 3. Add the face index offset again, and there you have it, a sequence that moves the bottom points towards the top ones. We have now completed all the possible variants, left, right, and top, bottom. Frame the nodes and call them top, bottom. It's now time to combine them all into one working asset. As I said in the beginning, each quad face gets duplicated, and each duplicate gets modified separately. The duplication part is easy. Select the group input, set position, mix vector and both its inputs, hit Shift D and make a new copy. We'll join these branches together for the final result. Add a join geometry node. Now let's combine our index series so that the left and top modify the first geometry branch and right and bottom modify the second one. This way we can decide if the subdivision will be horizontal or vertical. Don't worry, it will make sense very soon. Feed both left and top index series into a switch node, then connect its output into the index input of the evaluate at index node. Connect a modulo operator as the switching factor. Set the value to 2. The horizontal-vertical division type will be determined by the iteration number in the repeat zone later. If the iteration number is even, the face will be subdivided horizontally. Else, it will be vertical. We need to create a group input for the iteration number. Let me temporarily disconnect one input of the switch node so that I can easily add a group input using the input keyword. This way a new group will be created with the right data type, integer, and more importantly the group will not be listed on all other instances of the group input. This is a trick I always use to keep the node tree clean. Rename the group input to iteration, set the minimum value to 0, and connect it to the input of the modulo operation. Don't forget to reconnect the switch node. Repeat this operation to combine right and bottom into another switch node, driven by the same iteration group input. Now let's combine both mixing factors so they complement each other. Feed a new mix node into the factor input of the vector mix. Branch it way far. We will need to expand this, so we need some extra space. Leave the minimum value to 0 and the maximum to 1. Now get the complement to drive the other vector mix. Subtract the output of this factor from 1 and connect the result into the mixing factor of the duplicate vector mix. This factor now drives both polygons seamlessly. Now tab out of the node group and try increasing the iteration value. See, with each number, the subdivision switches from horizontal to vertical. We are on the right path so far. Tab back inside and let's automate the subdivision line animation using a noise. Connect the noise texture to the factor input of the mix node. You can immediately see that the setup breaks because we're generating a singular value per point. Set the noise factor to be evaluated in the phase domain instead. Set the noise type to hybrid multifractal. It's just a personal preference. You can experiment and use what you see fit. This noise generates values from -0.5 to 0.5. Add 0.5 to make it fit our 0 to 1 range. Now, I will show you a secret method to loop your noise seamlessly, so your recursive subdivision loops as well. By default, the noise texture gets the position of each face as a seed to generate its result. What if we take this position vector and rotate it a full circle during the course of our scene duration? It should animate and return exactly where it started, right? Let's try it. Insert a vector rotation. Let's rotate on the x-axis. Get a combine XYZ vector node. On the x input, connect a range map node and insert the scene frame number into its input value. We'll map time from 0 to the maximum number of frames into a new range from 0 to 360 degrees, or 2 times pi, or tau. Hit play and see the subdivision line move independently for each face. We may return and tweak these settings in a bit, but first let's do an overall test. Tab out of the group and insert it inside a repeat zone. Connect the iteration input to the first node's output. Also increment the iteration count by 1 and connect the result onto the out node. With each iteration, our iteration value will increase by 1. Now comes the moment of truth. Disable the Scale Elements node and lower the grid subdivision to 2. Increase the number of iterations and keep an eye on the 3D view. Hit play. Magic, huh? Not only is the original face subdivided several times, but the subdivisions are animated independently, giving the impression of some Mondrian painting. From here, it's just a matter of tweaking the noise settings a bit. You may have noticed that during the first couple of iterations, the subdivision lines don't animate. Lower the number of iterations to 2 and observe the quads not moving at all. That's because the first polygon position vector is at the center, so the noise doesn't get affected when we rotate it. We can easily fix that by adding some random vector value to the initial position. Add a random vector to the empty socket of an add vector node and watch the animation on the 3D view. If you think that the movement is too quick or jerky, the way to slow things down is by lowering the noise scale. We don't want to tinker with the time value now that we set it to loop perfectly. Set the scale value to 1.11. Tab out of the group and increase the iteration count. It seems to me that the speed of the animation increases with the iteration count, so I think it's better to expose the noise texture scale as a parameter that we can tweak from outside the group. There you have it. Now you can call yourselves the new Mondrians. Wait a minute, you might say. What about colors? Alright. I'll cover that too. It's simple and won't take much time to set up. After the repeat zone, append a store named attribute node. Call the attribute color. We'll store a random value for each face. The range will be from 0 to 3. That is 4 colors in total. Because almost everything in the shading realm is expressed in a range from 0 to 1, let's have these values fit within that range too. Divide 1 by them. Having done that, set a material for the geometry and hop over to the shading editor. We'll drive the diffuse color channel with the attribute we stored on the geometry called color. Insert a gradient ramp, change the interpolation type to constant, and add 3 new divisions. Distribute stops from the left and set the color for each one. Blue, yellow, red, and white. And that's it. I'm leaving it here. You can experiment at your own pace. I'm throwing some more ideas for you to try. Play with extrusion. Set it to random per face, or as I did it in one of my projects, drive the extrusion height by the area of each polygon. Currently this setup works with 4-point polygons only, but you can easily make it to work with triangles too. One small hint: any rectangle can be reduced to a triangle if you overlap 2 of the points together. Anyway, if you need to have the files I've demonstrated at the beginning, you can go to my Patreon page and contribute a small amount to support this channel. I usually don't share files because I think it's important to share the knowledge, but this way everybody who wishes has a way to show their appreciation. Thank you for watching, and as always, please share the knowledge.